In this video, I want to talk about graphing rational functions. When you're working with these problems, there's a lot of vocab that you need to be pretty familiar with, so I'm going to do my best to organize and define all that vocab in the beginning, and then we'll look at some actual examples after that. So first, I'm going to split these topics up into end behavior and discontinuities. So when we talk about end behavior, all we want to know is when you're looking at the graph, what's going to happen on the left end and on the right end. And if you just think for a quick second about on a graph, what's happening on the left and the right sides of the graph, well, over here, x is becoming a really big negative number, and over here, x is becoming a really big positive number. So what this translates into for us, like when we're actually doing these problems, we're just going to plug in big negative numbers or plug in big positives. And forget about the negatives, those are kind of crappy to deal with. So let's just plug in big positive numbers. So I'm just going to draw some quick sketches right here. You don't have to draw these with me, but what's going to happen with these rational functions is they might look something like this. So there's some weird stuff happening in the middle, but on each end they're approaching something, like they kind of level off and approach a certain number. Or sometimes we'll have a rational graph like this where it doesn't look like the left and the right end are approaching the same specific number, but it does have a slant asymptote. So in this case, we would say it's approaching that asymptote, whatever it is, and we'll talk about that in a minute. So let's talk about horizontal asymptotes for a second. This is a certain type of end behavior, and there's two ways that we can end up with a horizontal asymptote. So if the degree on bottom is bigger, we'll have a horizontal asymptote. So here's an example. We could have x squared minus 3 on top, and then like x cubed plus x minus 4 on bottom. So since the degree on bottom is 3 and the degree on top is 2, this one would have a horizontal asymptote. And by the way, it would be y equals 0. We'll talk later about how to get the horizontal asymptote, but I just wanted to say that for right now. And we could also have the degrees being the same on the top and bottom. This would also give us a horizontal asymptote. So again, for example, we've got x cubed plus 4x on top, so the degree is 3. And on bottom we have 2x to the third minus 1. So it's weird that there's a leading coefficient there, but it's important that the degrees are the same. In this case, the horizontal asymptote would actually be 1/2. Again, we'll talk about how to get that in a little bit, but for right now, I just wanted to get that there. But sometimes we won't have a horizontal asymptote, we'll actually have a slant asymptote instead. And these are kind of a special case because it only happens when the degree on top is exactly 1 bigger than on bottom. So the example I came up with here is 2x cubed minus x squared over x squared plus 4. So the degree on top is 3, degree on bottom is 1, so it's exactly 1 bigger on top. But maybe this is all sounding a little confusing because I introduced this by saying you're going to plug in big positive x values, and then I never even mentioned that here in these definitions. So let's talk about that really briefly. I like to think about it this way because I have a really hard time just being able to remember all of these three cases and then exactly how to find the horizontal asymptote for each one. So I just think about it this way because I'm pretty good at plugging in big positive x values. So looking at this first example, if I plugged in a really big value on top, I've got x squared minus 3 there. Let's say I plugged in like 1,000,000. Well, I'd have 1,000,000 squared, which would be insanely huge. That minus 3 is negligible. I can just get rid of it. I don't even have to worry about it. So it's really just like 1,000,000 squared. So it's a pretty big number on top. But let's think about plugging in that same big number on bottom, right? Now we have x cubed. So I'm going to take 1,000,000 and cube it. So 1,000,000 times 1,000,000, really big number. Take that and multiply by 1,000,000 again. It's going to get ridiculously large. And none of this stuff even matters anymore. It's just these terms that have the powers on them that are going to grow really fast. But on bottom, x cubed is going to grow a lot faster than x squared on top. So even though this is a really big number on top, this is a really big number on bottom. So if you take some number, whatever this is on top, and divide by a really, really big number on bottom, that's just going to get insanely big. This is basically just going to be 0. But compare that to what happens with this equation when I plug in really big positive numbers for x here. Again, I've got x cubed here, so this 4x really doesn't mean anything. When I plug in 1,000,000, I'm going to have to do 1,000,000 cubed, which is going to get insanely big, so the 4x, the 4,000,000, doesn't really mean much. But I'm going to have 1,000,000 cubed there, and 1,000,000 cubed here, except for this one, is actually times 2. So on top, it's like 1,000,000 cubed. On bottom, we have 2 times 1,000,000 cubed. So we had a pretty big number on top. On bottom, we have that same big number, the 1,000,000 cubed, but it's times 2, so it's like 2 times whatever the big number is. And if it's that same big number on top and bottom, it's the same number, we can cancel those out, and that's how I ended up with that 1/2. So I was actually looking at the leading coefficients. So now let's compare that to this last problem that we were talking about, the slant asymptote. If I plugged in a big number on top and bottom, again, this x cubed is the thing that matters. Even though x squared does have a power, it's not going to grow nearly as fast as the x cubed. So I can kind of just ignore that for a little bit. So on top here, if I plugged in like 1,000,000, again, I've got 1,000,000 cubed and then times 2. On bottom, I just have a million squared. So right now, the top of this fraction is growing insanely big, really fast. And yeah, the bottom is growing big too, but not nearly as fast as the top is. So the top is going to get really, really big, really, really big, and we're going to be dividing by a smaller number on bottom. So I'm not sure what value this thing is going to approach. That's why we can't just say y equals 5 or y equals a million or whatever it is. I'm not sure what value. It's just going to keep getting bigger and bigger and bigger. So that's why we have a slant asymptote. It's actually going to be approaching a certain type of equation. Okay, so for right now, just put this end behavior stuff on hold. We'll talk about discontinuities for a while and some other vocab, and then I promise we'll look at some actual examples. So I gave you this little way of thinking about end behavior over there. I want to do the same thing for discontinuities. So the word comes from discontinuous, right? So like a graph is not continuous. So think about graphing these rational functions. They look kind of like this. If you had to graph one, it would go, maybe down like this for all, well, but now I have to pick up my pencil to start all the way up here and start drawing from another spot. So a discontinuity is anywhere where when you're drawing the graph, you have to pick up your pencil to go to another part of the graph and then continue drawing. So just like end behavior was broken down into like horizontal asymptotes and slant asymptotes, discontinuities can be broken down into two types. Either it's going to be a vertical asymptote or it's going to be an actual hole in the graph. So let's talk about a vertical asymptote first. You guys probably heard about this before in previous math classes. A vertical asymptote is exactly what I have drawn here, this dashed line. And I like to think of these as the bad x values. So in this graph, I have every x value available. Like it's going to hit every negative x value to the left. It's getting really, really close to 0 for an x value here, right? Like x would be 0 right there. So it's getting really close to 0, but not quite there. And then over here, it's starting right next to 0, and then it's slowly getting more and more positive. So I have all of those x values. It looks like the only x value that I don't have, this is the bad x value in the equation, would be 0. So here's an example. Like if I had f of x equals 1 over x minus 2. Okay, this is a different example than what I have graphed over there. But if I had this function, if I plugged in 2 for the x value, right, if x was 2, what would happen there? So 2 minus 2 would be 0. I would have 1 over 0. And you should know you cannot divide by 0. That's really bad. So that means 2 is a bad x value. If I plug that into this function, that creates an undefined value. I'm not sure what 1 divided by 0 is. So since I can't plug 2 in, and since that's the only x value that I can't plug in, that's the only x value that would cause problems when I try to graph it, at x equals 2, there's going to be a vertical line there. So I just like to remind myself to just look at the denominator. If you're trying to find the vertical asymptote, look at the denominator. That's where the bad x values are going to come from, right? Because we can't divide by 0. I don't care what's happening on the top of the fraction, just the bottom. But another discontinuity, instead of a vertical asymptote, we can also have a hole. These come from when you take part of the equation out of the original problem. Or in other words, when we have factors that cancel. So here's an example. I kept the same x minus 2 in the denominator just like we had up here, just so that we can see the differences actually. Because in this example, the x minus 2 will cancel on the top and the bottom. So you would think that this would give us a vertical asymptote. I told you look at the denominator for your vertical asymptotes, but because we can cancel this factor, it's like we're taking part of the equation out, so it's like we're taking part of the graph out as well. So this factor x minus 2, the x value that goes with it would be x equals 2, right? Like if I plugged 2 in, 2 minus 2 is 0, this whole thing would go away. So now that I've identified that the hole is going to be at the x value of 2, but I'm not sure where, right? Like this doesn't tell me exactly where the hole is going to be. We want to write it as a point. So I'm going to cancel these factors out, which leaves me with just a 1 on top. And then I'm going to take this x value, I'm going to plug it back into this function and see what the y value would be for this hole. So it'd be 2 comma, and then there's nothing to plug in on top, it's just a 1. And then on bottom, 2 plus 3 is 5. So 1 over 5 is just 1/5. All right, so now I just want to use this example from our notes packet just to talk about what each of these things are, just based on this graph. So we don't have an equation to work with, but we can still do this visually. So domain is x values, and if I'm looking at this graph, it's going to go to the negative x values, it's going to go to the left forever and ever and ever. It's going to go right, oh, hold on, there's this hole here, so that's important. And then also, it's going down forever, but it doesn't look like it's ever going to have this x value, right? That vertical asymptote is never going to hit that. And then here it continues, and then it's going to go to the right forever. So it's going to hit every single x value, it's just there's a few problem x values. Right here, it's skipping over that one, and at this vertical asymptote. So for the domain, I'm going to write all real numbers, except x can't be, so I'm going to write an equal sign with a slash through it, x can't be this x value, well that's 1. So x can't be 1, And x also can't be whatever this value is. And that vertical line is at 3. So x can't equal 1 or 3, but it can be every other number. That's probably how you'd prefer to write it, but if you want to use interval notation, it would look like this. Start at negative infinity, go all the way to 1, but you can't include it, and then start at 1, go all the way to 3, but you can't include 3, and then start at 3, but not including it, going all the way to infinity. So it's a little bit obnoxious to write that out, but that's what it would look like in interval notation. Okay, so let's talk about range now. So range is y values, and if I look at how high up and how low down the graph is, right, we're looking at these y values, so it's going to go up to positive y values forever, and then it kind of evens out here. It looks like it's approaching this y value, which is 1, and then over here, it picks up right underneath 1, and then it goes down forever. Oh, there's this little hole we got to worry about, and then it's going to go down forever and ever and ever and hit all those negative x values. Or y values, rather. So again, it's going to hit every single y value. All real numbers are okay, except y can't be a few different values, right? Y can't be whatever this is, and that looks like it's right in the middle of the grid line, so I'm going to call that negative 1.5, so negative 1.5. And y also can't be whatever this value is, 1. If I wanted to write that in interval notation, again, it's going to hit all these negative y values, and it's going to go up, 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 up forever until it gets to negative 1.5, and then there's a hole there, so we can't include that y value. And then we're going to start at negative 1.5, and then go all the way up to positive 1, but we can't include that y value either, so I have to stop there, not include 1, and then go all the way to infinity. Now it's asking for the increasing interval. So if I'm reading this graph from left to right, just so I could read a book, where is the graph increasing or going up? Well, over here, it's going down. That's all decreasing there. And then when I start over up here, it's still always going down. So it turns out it's not increasing anywhere. I'm just going to put a dash there. And then for decreasing, I'm going to write all real numbers. The entire graph is always decreasing. All right, for this next one, you guys have been finding x-intercepts forever, but just as a reminder, we're probably going to label it as zeros. So when you see the word 0, we mean find the x-intercept. It's the same thing as finding the 0 of the function. So this graph just has one x-intercept right there, and it's the point negative 2, 0. It is a point, so I'm going to write it as a point, so negative 2, 0. All right, and this is where it starts to get confusing. It says discontinuities and what type? Well, we have two discontinuities on this graph. All right, there's the discontinuity, that's the hole. So let's identify that one first. So I'm going to say the type is a hole, and what is it, or where is it? So it's at 1, negative 1.5. So there's one of our discontinuities. The other one is this vertical asymptote, which is a line, so I have to write it as an equation. So I'm going to say vertical asymptote, that's the type of discontinuity. And then what is it? Well, it's x equals, in this case, it's 3. And then finally, it's asking about the end behavior, which remember, we said that's either a horizontal asymptote or a slant asymptote. In this case, there's definitely no slant asymptote anywhere on the graph. There's just this horizontal asymptote, which is the line y equals 1. So now that we've talked about all this stuff graphically, let's really look at an example with an actual equation and find some of these algebraically. Our first example will be f of x equals 2 over x minus 3. So let's start with the end behavior. Remember, that's really just like what's happening on each end. What happens when I plug in really big x values? And we can just think through that here, and we don't have to memorize anything. If I plug in like a million, so I'm going to have a million minus 3, which is really close to basically just being a million. And then if I have 2 divided by basically a million, that's really close to 0. And if I plugged in like 100 billion, that would be even closer to 0. So the bigger the x value gets, the smaller this whole thing gets. The value of the function gets really close to 0. So I'm going to say it has a horizontal asymptote of y equals 0. If I wanted to know about the discontinuities, remember there's two types of those. It can either be a vertical asymptote or there could be a hole in the graph. Well, holes in the graph only come from if I have a factor on top and bottom that I'm canceling. So if you're getting rid of part of the equation, you're getting rid of part of the graph. There's definitely nothing that's going to cancel here, so I know there aren't any holes in the graph. There is a vertical asymptote though. So if I plugged in an x value of 3, 3 minus 3 would be 0. That would be bad. I can't have the denominator be 0. So if I plugged 3 in for x, that's my vertical asymptote. X equals 3. Maybe you haven't seen this pattern yet, but the domain will always refer to, or it'll always kind of match up with the vertical asymptote. So in this problem, I can plug any x value I want in, I just can't plug in 3. So when I'm writing out the domain, I'm just going to write all real numbers except 3. So x can be all real numbers, it just can't be 3. So these things match. They're just kind of opposites, I guess. Same thing for the end behavior and the range, because this is talking about y values just like the range. So if I'm writing the range out, the y values can be anything except there's an asymptote at 0. So the graph is just going to get closer and closer and closer to that asymptote, but it's never going to touch it. It's never going to actually hit 0. So the range is also all real numbers, but y can't be 0. A lot of times we'll ask about the x-intercept as well, so let's take a look at that here. It's just, this is kind of a weird example because of this. The horizontal asymptote is y equals 0. So if I were to graph that just really quickly, I know there's going to be a horizontal asymptote right here on the x-axis. That means that I'm not going to have any x-intercepts because there can't be any points on this asymptote. So this is kind of a weird special case, but in this instance, there's actually no x-intercepts. All right, so here's our next example. 2x minus 3 over 3x plus 4. We'll start with the end behavior again, which is either like a horizontal asymptote or a slant asymptote, and we just kind of think of that by plugging in big x values. So looking at this example, if I plug in like 1,000,000, let's just use that as our example. Well, on top I'd have 2,000,000, and this minus 3 would just kind of go away. If you have $2 million, if someone steals $3 from you, you're not going to care, because the $2 million is huge. Same thing on bottom, you're going to have 3 million here, the plus 4 isn't going to matter. So it's really like we have 2 million over 3 million. Well, 2 anything over 3 anything of the same is 2/3. So for the end behavior, we're going to have a horizontal asymptote. It's going to approach that value, 2/3. So it's going to be y equals 2 over 3, which again, that's the leading coefficient over the leading coefficient. So we have the horizontal asymptote. Let's take a look at the discontinuities, which will either be a vertical asymptote or a hole if we can cancel any factors. Well, I don't see any factors that are the same on top and bottom, so we can't cancel anything. That means there's going to be a vertical asymptote. We just got to figure out what it would be. Again, look at the bottom. Look at what's going to go bad. Like, what could I plug in for x that would be really bad in this instance? Well, this is a little bit tougher just because there's a lot more numbers going on. So I know that I can't have this thing be 0, right? The bottom can't equal 0. That's bad. So let's actually just solve this little mini equation and see what x value makes that 0. So I'm going to say 3x plus 4 equals 0. Subtract 4, divide by 3. So x equals negative 4/3. That's our vertical asymptote, x equals negative 4/3. Now this one I think will have an x-intercept because the horizontal asymptote isn't on the x-axis anymore, it's a little bit above it. So there's going to be a spot where the graph does actually cross the x-axis. And let's figure out where that is. The one thing you need to remember about x-intercepts is I don't know what the x value is, but I know the y value has to be 0. Again, that's because the x-intercept has to be on the x-axis somewhere, so the y value would have to be 0 there. That really helps us because then I'm just going to take this function and set it equal to 0. So 0 equals 2x minus 3 over 3x plus 4. And what's really awesome about this is when you have a fraction equals 0, the bottom doesn't matter, right? If a fraction equals 0, that just means that the top has to be 0. The bottom could be any value it wants to be. So I'm actually going to simplify this and just solve this equation. 2x minus 3 equals 0. So I'll add 3 over to the other side, and then divide by 2, so x equals 3/2, and that's the value for our x-intercept. So I guess I forgot to talk about domain and range, but remember they're just very related to the horizontal and vertical asymptotes. So if we said the vertical asymptote is at x equals negative 4/3, that means that x can be all real numbers, except it just can't be negative 4/3. Same thing for the range. If we're saying that the horizontal asymptote is y equals 2/3, that means there's never going to be any points there. So the range is all real numbers, y can be anything, it just can't be 2/3. And I just wanted to go through one more example to show you what's going to happen in this case. So now we have the degree on top being exactly 1 bigger than on bottom, so this is the example where we're going to have a slant asymptote. So in order to find that slant asymptote, we actually have to do a little bit of long division, which really doesn't take that long, and you can use the box method for it. So I'm going to put x squared plus 2 on the outside, and then the first term is x cubed inside, and let's see what happens here. So x cubed goes in x times and then multiply, so we would get 2x, but there were no x's there, so that means I need to fix this by subtracting 2x. All right, so then x squared already can't go into negative 2x, so we're already at the remainder stage basically. And I don't care about the remainder, and it's kind of the same reasoning as we were doing with like the plugging in big numbers. Like if you plug in 1,000,000 here for x, you're going to get 2 million, and then the negative 3 doesn't mean anything anymore. It's the same thing here. Our slant asymptote is just the quotient, like the answer to the problem, and we don't care about any remainder stuff. So in this case, the slant asymptote is really just y equals x. So I'm going to say SA for slant asymptote, y equals x. All right, now we need to talk about discontinuities. Again, that's either a vertical asymptote or a hole. And I guess we haven't had any holes in any of these examples because we haven't had any factors that cancel out. Looking at this one, we've got x cubed minus 4 on top. That can't be factored, but if it could, you need to factor it so that you can potentially cancel those factors. But this one can't be. And x squared plus 2 can't be factored. So I know I don't have any canceling factors, so I don't have to worry about a hole in the graph, but I do need to worry about a vertical asymptote. So remember, just look at the denominator and set that equal to 0 and see what bad x values there are. Well, actually, x squared plus 2, if I set that equal to 0, I'd have x squared equals negative 2, and I can't take the square root of a negative, or I can't get a real number out of it anyways. So this actually doesn't have any vertical asymptotes or holes. It's kind of a weird case. So I'm just going to write none for discontinuities. And as far as an x-intercept, remember, if we have a fraction that's set equal to 0, I don't care what the bottom is. It could be any value down there. I really just want to set the top equal to 0, and that will make the value of the fraction 0. So I'm going to say x cubed minus 4 equals 0, and solve that quick. So I'm going to add 4 over to the other side, and then just take the cubed root of it, and I don't know what that value is, and I really don't want to deal with a decimal, so I'm just going to leave it as the cubed root of 4. You could type that into your calculator and get a decimal out. That would probably be more practical, but this is exact. All right, so let's just talk about domain and range real quick, and then we'll be done here. This is a weird example, because if you look at the end behavior, the horizontal asymptote, there's no horizontal asymptote. That means that there isn't any single y value that the graph will never approach. It's going to actually hit every single y value. So for range, it's actually just all real numbers. There aren't any problem y values. And likewise, we said there weren't any problem x values. There's no holes, there's no vertical asymptotes, so the domain is also all real numbers. So I apologize, this is a bit of a longer video, but hopefully this gets you going with understanding rational functions.